NASA built a tunnel where falling aircraft stop falling. That is not a camera trick. In Hampton, Virginia, a column of air can rise at up to 117 miles per hour. Drop a scale model into that flow, and gravity can hold it inside the test section while cameras and engineers watch what the aircraft does next. This is NASA Langley's new Flight Dynamics Research Facility, the agency's first major new wind tunnel in more than 40 years. The first hard number is 20 feet. That is the diameter of the vertical test section. It stands 24 feet high inside a building that rises 131 feet. The entire facility covers 25,000 square feet, yet the objects at the center can be small enough to hold in your hands. The reason is simple. A conventional wind tunnel usually fixes a model in place and pushes air past it. This vertical tunnel lets a free-flying model move. If the air pushes upward with roughly the same force as the model's weight, the model can remain inside the chamber. Engineers can then observe instability, a stall, a tumble, or a spin without risking a pilot or a full-size vehicle. So here's the question. Which should NASA test first? A drone, a re-entry capsule, or an experimental aircraft? Hold your answer, because the oldest machines behind this facility point to the most surprising one. NASA's Flight Dynamics Research Facility does not begin from zero. It consolidates two historic Langley facilities: the 12-foot low-speed tunnel, which began work in 1939, and the 20-foot vertical spin tunnel, opened in 1941. NASA says rigs, instruments, and data systems from those facilities were repurposed for the new building. The replacement is new, but much of its research memory is not. That matters because the old vertical tunnel completed more than 600 projects by its 80th anniversary. Researchers used scale models to understand how aircraft entered spins, whether control inputs could stop them, and how unfamiliar shapes behaved in free fall. Historical photographs show everything from early aircraft models to Mercury-era capsule work. Those images are legacy research, not tests already completed in the new tunnel. The new machine also solves a very modern problem: repeatability. Its air can run from 0 to 172 feet per second, and NASA says the flow is actively cooled to 79 degrees Fahrenheit. Stable temperature and controlled speed help teams compare one run with the next instead of wondering whether the tunnel itself changed the answer. And this is not only about airplanes. NASA lists drones, autonomous flight, X-planes, atmospheric entry vehicles, and parachute or recovery systems among the possible uses. The same physics can support studies connected to Artemis return systems and to concepts meant for thick atmospheres such as Venus or Titan. None of that means those missions have already flown here. It means the facility can test the dangerous part before reality gets a vote. That is why NASA's scheduled ribbon cutting and showcase matter. NASA is not unveiling a machine that makes gravity disappear. It is building a controlled place where gravity, airflow, and unstable motion can meet in full view. The strongest result may not be a model that flies perfectly. It may be the one that fails predictably enough for engineers to understand why. The paradox is the point. Make a falling vehicle appear motionless, then study every motion it is trying to hide. If you chose the re-entry capsule, the legacy evidence is on your side. And if you want the next chapter in NASA's quieter flight experiments, watch the X-59 story on the end screen.